Okie dokie, everybody. So today we're going to finish up our igneous rocks, and then we're going to get into sedimentary rocks. Okay, so let's go ahead and look at our logarithmic scale that we left off last time. So here's our scale where, again, this is logarithmic. This is why it has all these funny spacings going on here. Again, these intervals change, and that's what's weird about it. So if we look at our x-axis here, right? This guy's our x-axis. And he goes by 1, 2, 3, right? This is an even interval all the way across our x-axis. But we start from 0.01 years and go all the way to 1,000 years, and the interval does change. So from here to here, the intervals increase by 0.01. From 0.1 to 1, it increases by 0.1. From here to here, it increases by 1. From here to it increases in intervals of 1. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then from here to 100, it increases by intervals of tens, 10, 20, 30, 40, 50, 60, all the way up to 100. Then from 100 to 1,000, they increase by an interval of 1,000. So there's 10 lines in between each of these intervals. So that's what the logarithmic function is. Because if we just started out with this increase of 0.01 and we counted and we did these lines for every 0.01 and we tried to get to 1,000, there would be I think would be 100,000 lines, I believe, would be on here, which obviously my screen would need to be ginormous to fit that on there. So that's why we do this. Okay? So then what we need to do now is we need to graph these guys. We need to run our line through here. And I'm going to do my best job with my marker. And we're going to trace it all the way up here. Whoa! I missed my last point, but that line should run right through here. But anyways, your graph should look like this. So if you need to pause and take a look at it, here's 24 years right here and 4.3 centimeters. Here's 110 years here and 6.4 centimeters. Here's 565 years and 8.8 centimeters. And then here's 997 years and 10 millimeters. Okay, if you guys need some help with that. So let's go ahead and move on to this. We're going to focus on our graph. So what the heck is our graph doing? What's the relationship with our graph is pretty much what it's asking here. So what is our relationship between the time it takes a rock to cool and the crystal grain size? So if we come back here and look, well, as our crystal grain size gets bigger as we go from left to right, and then as the years go on, right, our time goes on, these crystals actually get bigger. Okay, so what's that? The longer magma cools, the larger the crystals will be in the rock, the igneous rock, right? So we're talking about igneous rocks right now. I had a couple kids during class today. They seem to be using just rock. They said the longer it takes for the magma to cool, the larger the rock will be. No. So a rock could be as big as this, or a rock could be like the size of a bus, or even bigger than a bus, right? So we're talking about the crystals inside. So I don't know if you guys can see these little guys right here, but you can see these. This is a nice piece of granite here, where you end up seeing these different guys, and these are our crystals in here. And these are actually some pretty good sized crystals in here, which would definitely indicate that this guy took a really long time to cool. Here is another kind of igneous rock, and I don't know, you really can't see it all that well with this, but you can see some dots, or it looks like air bubbles almost, like right here, some of these guys. But wherever you see those speckles, okay, those speckles are actually little crystals, okay? So they're smaller, so that it would indicate that this pink guy right here cooled faster than this guy that has these crystals that are very easy to see, okay? So let's keep moving on. So then it talks about obsidian. So we have, what's the relationship between texture and crystal size? And so when we're talking about texture, up here, right, it's saying, is it fine? Is it fine or is it coarse? Meaning rough. So is it so fine? When I think of fine, or like it's smooth, it's a smooth surface. If it's coarse, that means it's really bumpy and it feels like a lot like rough sandpaper. And then crystal size over here, again, it's talking about the size of a crystal. Is it big or small? And that's kind of the verbiage we use for crystal size. And so again, if I'm looking at my glassy obsidian, I'm videoing right now. And so I have this obsidian here, and so this guy has like the texture on it's very smooth, but it's a glassy surface because it doesn't have any grains in it. Like they don't form, there's no crystalline structure to it. So that's where this guy is over here. And then we get into some other guys like this basalt. Okay, and you'll read about basalt, or you probably have already read about basalt. This guy is really common on the sea floor. We don't see it a whole lot because we don't live on the sea floor, but this is our basalt right here that has a fine grain. I can feel it. I can feel a little bit of the grain, and like I said, it's really, really fine, and it feels smooth. But then as these grains get more coarse or gets more rough, my crystals get larger, right? So I start looking at this guy, and I can start feeling this is a lot more coarse. It feels like rough sandpaper. Here's another type of some kind of granitic rock. It gets harder and things like that as well. And I don't know if you guys can see. It doesn't really glisten all that well. I don't know if you guys can see the light kind of glistening off of some of the crystals in there, but they do. Okay. And so what's the relationship between texture and the crystal size? Well, it's the same. So we could say that the more coarse the texture, the larger the crystals will be. Okay, so really no crystals here in obsidian, but then basalt, these guys form really quickly. So the crystals, they could be some, but they're microscopic. It's hard for us to see with the naked eye. And then as we get to granite and this pegmatite, these guys are easily seen with the naked eye, and their texture is also rough. So then what's the feature in igneous rocks that is best of the indication of how rapidly the magma crystallized or cooled? It's the grain size would be the best one. Not mineral composition. A lot of kids thought mineral composition, but minerals will be in magma no matter what. So just because I take this guy right here and I throw it into magma, and then all of a sudden the crystals that were in here, or the minerals that were in here, right, the compounds, they don't go away. They don't just disappear, right? The law of conservation of mass, that's just not going to disappear. So the minerals will still be there, but it'll just be in liquid form. It won't be in solid form. And so it doesn't have anything to do with mineral composition. It's actually with the grain size. So the bigger the grain size, that indicates the longer that has been cooling. And so right here gives you a nice igneous rock definition of what an igneous rock is. Okay, here we start talking about igneous rocks. The movement of magma to a new position is called intrusion, but it wants to know what an intrusive rock is or a plutonic rock is. And so it gives you this term, it gives you the name. Pluto was named after the Roman god of the underworld, right? And it says right here, as mass cools and crystallizes, it slowly forms granite. Because coarse-grained igneous rocks such as granite form deep underground, they're classified by origin as intrusive or plutonic. So what's the definition? The definition of this guy is rock that has formed beneath the surface of the earth. And then vice versa, essentially down here when we start talking about this extrusive rock is rock that is formed above the surface. Okay, extrusive, exit, outside. volcanic thing about something spewing out, but this basaltic rock that it starts talking about, this is on the sea floors. This actually, so like when you think about islands that form in the ocean, like the Hawaiian Islands and things like that, tropical islands, they form from volcanoes that start on the floor of the ocean and they erupt, and then, thousands of years later, they start turning into islands like the Hawaiian Islands, and they've all been made out of this type of rock, this basaltic rock. And again, it's those crystals are microscopic. Based on the passage, is there a relationship between crystal size and intrusive and extrusive rock? Yeah. So if rocks are going to form within the Earth, are they going to cool quickly or are they going to cool slowly? Well, they're going to cool slowly if they're intrusive, if they're within the Earth, right? So rocks formed within the Earth cool slowly and produce large crystals. So within the Earth, right? If they're within the Earth, that means they must be intrusive. Let me put that here. Intrusive rocks formed within the Earth cool slowly and produce large crystals, and then it's vice versa. For extrusive. Right? So what we would say is extrusive rocks formed outside the Earth or on the surface of the Earth cooled quickly and produced small crystals. So it would just be the opposite of this phrase that we wrote here initially. I'm going to go ahead and mark this one out. This one's asking the same thing like 5 times over. Here, it asks you just to construct a graph. And so, again, we have our y-axis here. We have our x-axis here. And so this is actually where our dependent variable goes. So if you're dependent, you change based on somebody else. So somebody determines what you do. Your parents determine what you do. Independent means you do your own thing. You decide what you do. And so here we have cooling time. Ooh, I just meant to underline that. Cooling time and crystal size. And so we have 2 variables here. We have 2 axes here. So crystal size depends on the cooling time, right? Because the longer it takes for it to cool, the larger the crystal. Cooling. So cooling time, crystal size. So time doesn't change for anybody. Time goes on no matter what. And then what's our graph going to look like? What's our trend of this graph? As time increases, crystal size also increases. Therefore, our graph would have this kind of positive trend to it. Okay, and then I handed out this as homework. So you guys need to go ahead and finish 1, 2, 3, and 4. And I'll go ahead and grade that when you guys get that turned in. All right. So it's going to ask you some stuff. So if we look at, I'm going to go over some igneous rocks here real fast. All right. So I have this guy right here. And if you could see, he's got a lot of pores in him. He's actually super, super light. This is called scoria. Scoria. And then I also have pumice right here. And you can also see a lot of holes and a lot of air pockets, I guess. And so what was going on when these guys formed is these guys were actually shot right out of a volcano, and they were cooled almost immediately once they left the volcano. So magma and lava actually act like soda. And so you know that you have a soda, and if you shake up that soda, you're going to have a lot of fizz with it because carbon dioxide is compressed inside of your soda. And if I shake it up, then it builds up all this pressure, and then that carbon dioxide wants to get out. That's the same thing that goes on with magma. There's dissolved poisonous gases inside of magma and lava, and then as we release that pressure, as in it's erupting, so that cap of the volcano has essentially come off, it can start bubbling up because all of these gases are releasing. Well, anyways, these guys still have some of those trapped gases in them, and they cool so quickly that they harden around those air pockets, those gas pockets, and they produce all of these air pockets. And these guys actually pumice can actually float on water because it feels like a Cheeto puff in my hand, like I could just squeeze and crush these guys. So these are igneous rocks. They have a lot of holes in them. They have air pockets in them because they cooled so fast that they trapped the air or the gases that were trying to escape as that erupted. So that's how fast these guys cooled. Where these guys like igneous, this kind of granitic rock, or this guy right here that you can easily see those crystals in, they took possibly tens of thousands of years to cool, which allowed all of these crystals or these little molecules to come together over a course of tens of thousands of years to form those larger crystals. All right, moving on. So I skipped this part. I won't have this for you guys to do. I'm not going to take it for a grade, but we had to get going in class. We're going to have a test on next Thursday, and so we still have to do sedimentary rocks after this. So I'm just kind of moving through some stuff before our test on Thursday. What I asked you guys to do is to look at this. This is going to help you with your homework that I gave out today. So it's on page 4 of the ESRT practice. And it shows you how to use this, and that's all it's asking is how to use this. So if you remember your mineral ID lab, it had this flow chart. Is it metallic? Is it non-metallic? Okay, it's metallic. Now is it hard or soft? Okay, it's hard. Now, what's the special property? It's magnetic. Okay, and then you look under that and it says magnetite, and it helps you identify what kind of mineral that is. This is the same way. Okay, what kind of texture does this rock have? And this is sedimentary rock, right? Down here it has igneous rock, so granite. All of these guys. This one's a little harder to. It talks about texture right here. Don't worry about this one. This one's super tough, but this is a nice little diagram here for the rock cycle. You follow all of these arrows and stuff like that. It shows you how they get it to be made in sediments, or go from igneous rocks to sediments, go from igneous rock to metamorphic rock, go from magma to igneous rock. Don't really need to know about this guy. But yeah, let's go ahead and start on sediments. So you guys have already read this part about sediments, sedimentary rocks. Most of them are made from weathered remains of other rocks. And so we call these other segments of fragments of other rocks, we call this clastic or fragmental. Okay, and so something good is like this guy right here. So that's not what I want. So I have this conglomerate guy, and we can actually see like this is a, here's a pebble. Like this is a pebble, and then we have a whole bunch of other sand. We have some more pebbles in here, so we can see actual different parts of rocks, different parts, different particles of sand in this guy. And so those are fragments of other things. Here, a fossil is actually a fragmental rock. There's fragments of other guys in here that we can distinctly see, right? So we see this nice little spiral-shaped fossil in here. Here's some limestone. So you can see a shell pretty nicely right here. You can see a little bit of a shell right here. You can see some other shells also on the back side of this guy. So there's fragments. We can see distinct parts of other things in this. So that's what we call fragmental or clastic. Okay. And so those are sedimentary rocks, and sedimentary rocks is exactly what it sounds like. These rocks are made up of sediments. And so how do we get sediments? Well, we get them from other parts of other rocks being broken down, essentially. So igneous rocks are weathered down. They can be broken apart with ice, water, rain, snow, wind, and stuff like that. And then they're carried off, and then millions of years later, they're compacted, they're cemented together, and then they form, these conglomerate rocks that I'm showing you here. Okay, or they could look like other things, like a siltstone. Okay, so let's take a look at this. So you guys should have already read this. So that's why fossils. It talks about the process to create igneous rocks and metamorphic rocks. So igneous rocks come from cooling magma. So obviously if we turned any fossils into magma, then the fossil would just be gone, right? It'd be completely wiped out. Metamorphic rocks, you subject something to intense heat and intense pressure for thousands of years or millions of years. That's definitely going to change that fossil and wipe it away. And you'll never, usually, right? It says usually you won't see that. Igneous rocks, I'll go ahead and say if something's melted down, you will not find that fossil ever again. So it keeps on talking about clastic rocks. Clastic and fragmental are classified by size of sedimentary particles from where they are formed. So we'll start talking about like the sandstone here. And so if you can see, it's called a sandstone because it's actually made from sand. So you guys have seen striations, or these layers that you see. You can kind of see these layers, these different bands of dark and light colors. And this is sand. But it just took millions of years for this cementation to happen and compaction to happen to now make this into a sandstone. So the particle size for this is sand, and you'll see that on your paper when we start talking about your homework. You'll see what particle size they designate sand with. It's pretty small. What am I going to do here? There we go. Okay, and then it talks about bioclastic. Bioclastic, when we look at bioclastic, bio, like biology, means life. So when I showed you, this is a sample of limestone that has these shells in it and stuff. If you can see these shells, that would be bioclastic. It's formed from material made by living organisms, or this fossil that I was showing you earlier here too. That is definitely a bioclastic rock. Even coal. So coal is considered a rock. So organic material. So remember, minerals had to be inorganic, meaning they did not come from living things. Rocks can be inorganic or organic. Now, coal is, and you'll read about it next page right here, as you should have already. Coal, where plants grew, they died, they accumulated upon layers and compressed, turned to stone, and now that is a sedimentary rock. Here's our conglomerate guy we were looking at. Here's that sandstone I showed you guys. Here's some shale. You guys have probably, if you guys ever went creek walking before, this is a very common rock to find in there. It's this black stone that usually breaks in thin, kind of flat pieces, and you can throw them. They can come big or small. This is a very common. If you might be able to look at it closely, you can kind of see some layers in there. And this is made from silt or clay, particles of silt or clay. And so we'll talk about these guys here in 1 second. And so generally, anytime you can see layers being made from these rocks or stuff being put together, we can definitely tell that that's sedimentary rocks, because sediments are parts of other things that have been broken off of other things. And now they have rejoined with something else or other things to make a new rock. Okay. So it says right here, what are 3 types of textures possible? So this is where you're going to do this ESRT practice. Again, here's where I have this guy right here. See if I can zoom in a little bit. Okay, so it says texture right here, right? This is the homework I assigned everybody today. We didn't get all the way through the packet. This is where we ended up stopping. So it says, what are the 3 types of textures possible? And so you will find that on our texture. So we have clastic, crystalline, bioclastic. Okay. Here, limestone actually can have 2 types of textures. It can have a crystalline structure. So here you see the composition: halite, gypsum, dolomite. These guys should look very familiar because they were minerals. It says crystals, so you'll see crystals in these guys. So what that means here is this limestone that I've been showing you guys. So again, this limestone down here, crystalline or bioclastic limestone. Again, this guy right here has these, we can see these shells in here. And so that's that bioclastic. We see fragments. We see some other evidence of living organisms that made up this rock and have now turned to stone, right? Where, let me see here. Here's another example of limestone. But this is our mineral composition one. There's no sign of any fossils in this guy. It said this is made up of calcite, so it has a lot of calcium in it, meaning if you guys remember calcite, it actually reacts with hydrochloric acid. So this is one guy that limestone can look totally different from sample to sample. But that's what it means by this is a crystalline form of it, meaning it's just made up of these particles and things and little small crystals, itty-bitty crystals. Let me see what else. What else? Talks about, okay, let's talk about grain size here. So anyways, I was talking about these clastic guys that are identified by grain size. So here, pebbles, cobbles, boulders, embedded sand, silt, or clay. So actually, if we look at these three guys right here, sand, silt, clay, sand is actually kind of the bigger one out of these guys. Sand particles, you guys know what sand is. The sandstone here, it's made out of sand particles that are between 0.006 centimeters to 0.2 centimeters. And then something like siltstone, rightfully so, called siltstone because it's composed of silt. And so if you ever go to the bottom of your pond or something like that, and you take a handful of whatever's at the bottom of your pond, it's like black, nasty gunk, that's silt. That's just very fine particles that have settled at the bottom of your pond over the years. And that's even smaller than sand. That's 0.004 to 0.006. And then clay is actually a particle. Clay particles are incredibly small. They can be really compact. You guys know, if you guys dig down about 3-4 feet anywhere around here, you'll run into clay, and it's really hard to dig through. That's because it's super compact. It's so compact because of these particles. They can fit so tightly together because they're so small. And these guys make things like shale that I was showing you guys earlier. And these guys will layer on top of each other, and they'll form that sedimentary rock shale just like this. And then this conglomerate, we talked about conglomerate, or breccia is a very similar to conglomerate, but this conglomerate has smooth river stones in it essentially, where breccia has like sharp angular fragments. So these guys actually have pebbles that can be like a centimeter long, or boulders. And they actually define boulders as like something that's the size of a softball or bigger. So a softball-sized rock, like we call that a rock, but in geology, that's actually considered a boulder, all the way up to, like I said, the size of a bus would be a boulder, even bigger than that. But anyways, I had you guys do all that. So go ahead and finish this page up, and you guys should be able to do the rest of this. Actually, I had you guys don't do 30. Don't do 30. What else? D. I could not find D for this one. So it says, what's this one? D. Do not do it. You'll want to watch that video I put on there on limestone rocks and how they form cave formations, and you can do that. And go ahead and get this guide done when you're for today. But like I said, in class, we'll get this finished. I'll make another video, and I'll go over everything else, all of that stuff that I just assigned to you guys. Okay? All right. Message me if you guys have any problems. Like I said, we will have a test next Thursday, and you guys will have to take it at 10 a.m. like usual. Bye.